Good morning everyone, and welcome to today's worked exam answer video. Today I'm having a look at a little bit of an organic synthesis question, although it is focused around two specific compounds, propanal and propanone. However, we are being asked quite a few different things about these, so we've got to think about how we can distinguish between them with a chemical test, how we can distinguish between them by counting up the number of peaks they would have in their proton NMR spectra. Then we've got this little bit of a synthetic pathway where we've got the aldehyde and the ketone. We're doing two individual processes on those to make X and Y, and then X and Y come together to make Z. We have to identify what X and Y are, and we have to think for each of those three steps what type of reaction is occurring, what reagents we would need, and what conditions we would need as well. And that final question is worth 10 marks, but it is quite straightforward where they're coming from because we've obviously got three different steps to deal with, and we have to identify X and Y. So I'll do my annotations as always, and my worked answers and my highlighting, and I will come back to you and explain everything. Okay guys, so it tells us that we have to describe how propanal, CH3CH2CHO, and propanone, CH3COCH3, can be distinguished using a chemical test and then the number of peaks in their proton NMR spectra. So propanal is an aldehyde, and one thing just to quickly mention about aldehydes, we don't write the functional group as COH. That could be confused for an alcohol, shouldn't be, but just to be sure, bizarrely we do put the H in between the C and the O in the structural formula, so that's a big clue that you got an aldehyde as well as the ending of al, propanone, ketone, C double bond O's in the middle of the chain. Now there's two different chemical tests we could use here. There's Tollens reagent and Fehling solution. Personally, I prefer Tollens reagent because the mark schemes will always say for the positive result with an aldehyde that a silver mirror forms. My issue with using Fehling solution is that the colour of the precipitate does vary between different mark schemes. I've seen orange red, I've seen brick red, and that makes me a little bit nervous. Whereas when we add Tollens reagent, every time we add that to an aldehyde, so in this case the propanal, we'll get a silver mirror forming, and with a ketone, like propanone here, we would get no visible change. Please don't say nothing or no reaction. There may be reactions going on, we just might not be able to see them. That isn't the case here, but just as a general rule of thumb, no visible change, no observable change is the best sort of answer you can put where there is no positive identification in the test. And that's worth 3 marks. You're going to get 1 for the reagent and 1 for each observation with the propanal and the propanone. When it then comes to the number of peaks in their proton NMR spectra, I thought the easiest thing to do would be to draw out propanal and propanone. So the number of peaks corresponds to the number of different hydrogen environments. So we need to think about which hydrogens are in the same environment and which hydrogens are different. And I've colour-coded them on the aldehyde to show that there are 3 different hydrogen environments. The 3 on the end, on that carbon, they are in a different environment to the 2 next door, because the 2 that I've gone round in blue are directly adjacent to the C double bond O, whereas the ones that I've gone around in the purple aren't. So they're different from each other, and yes, this pink one is also adjacent to a C double bond O, but it's then not on a carbon that's adjacent to a C double bond O for starters. So they are your 3 different environments, whereas with propanone, because of the symmetry that we have with this particular ketone, we've got the 3 hydrogens on a carbon either side of the C double bond O, and there's a plane of symmetry that would go straight through the C double bond O like that. That means that there's actually only 1 hydrogen environment here, because all hydrogens are on a carbon that's adjacent to a C double bond O that then has another CH3 on the other side of that. So there's only 1 environment there, whereas with the aldehyde there's 3, because there's no symmetry there, because the aldehyde group has to be on the end. So that's how we can distinguish between them, by looking at the number of peaks in their proton NMR spectra. Then we have this little synthesis where compound Z can be produced by the reaction of compound X with compound Y, as shown in the synthesis outlined below. So we're taking the propanal and the propanone that we started with, we're doing steps 1 and steps 2 to each of those respectively to get X and Y. We're then adding X and Y together in step 3 to get Z. So what I've done here is I've annotated that we have an ester functional group in there, so the C double bondo, C single bondo, and when we form esters, the first part of the ester before the C double bondo, including the C double bondo, comes from the carboxylic acid, and the part that comes after the single bonded O and the O come from an alcohol. And that gives you a massive clue as to what we need to be doing with the propanal in step 1 and the propanone in step 2 to get X and Y, because we need X and Y to be a carboxylic acid and an alcohol. And yes, we could turn propanal into an alcohol, but that wouldn't be the right alcohol, first of all, because if we have a look at the structure, the OH group needs to be on the middle carbon, and from an aldehyde we can only make primary alcohol, so that's not right. And even if that was the alcohol, ketones cannot be turned into carboxylic acids. So we need to know about the products of oxidation of aldehydes and ketones and the products of the reduction of aldehydes and ketones. So aldehydes can be oxidized to carboxylic acids, which is what we're going to do here. They can also be reduced to primary alcohols, which is not what we need based on the structure of Z. Ketones cannot be further oxidized, so can't be turned into carboxylic acids, but ketones can be reduced back down to secondary alcohols, which is exactly what we need here, because there's my longest chain of 3 carbons and the OH was on that middle carbon there, carbon 2. So that means that step 1 is going to be oxidation and step 2 is going to be reduction, and then we're going to join those together via esterification, which is step 3, to make this ester. And we are asked to name the type of reaction involved for each step. Now, type of reaction and name of mechanism are different, and I believe I've touched upon this before. Oxidation is a type of reaction, reduction is a type of reaction, esterification is a type of reaction. How step 2 occurs is via nucleophilic addition. That is the mechanism by which the reaction occurs, but the reaction itself for step 2 is reduction. So it's important that we understand the difference there. We have to identify compounds X and Y. So I've done that in 2 different ways. So via structural formula, following their example for the aldehyde and ketone. I've also named them. You could have drawn them. It just says identify. So they've been quite broad there. Obviously, if they say draw the displayed formula or draw the skeletal formula, make sure you do. If they say identify, you've got a bit more scope for however you choose to do that. So make life easy for yourself. We also have to give the reagents and conditions, and it tells us equations are not required, which is lovely. So when we're dealing with oxidation of an aldehyde to a carboxylic acid, we're going to need to be using acidified potassium dichromate as our oxidizing agent. And to ensure all the aldehyde is converted, we may as well heat under reflux. We don't necessarily have to, but it makes sense because that's going to ensure that we get the best yield of X. We're not going from a primary alcohol. If we were, we'd have to heat under reflux. We don't need an excess of the oxidizing agent because we're only oxidizing the aldehyde once. So that's all we would need for step 1. For step 2, which is reduction, we're going to need the NABH4, which is our reducing agent, and that gives you the H- nucleophile, so you can then do nucleophilic addition, which we're not asked for here, but just so you know. And again, we tend to do this reaction by heating under reflux, and again, that's going to ensure maximum yield of alcohol is made at the end. And then esterification, so combining our alcohol and carboxylic acid together, we need a catalyst, which is concentrated sulfuric acid. That should cover all of the points in that final 10-mark question, and quite a lot of different organic concepts tested there, but in what I feel is quite a nice question if you know your stuff. Any questions at all, as always, please just get in touch, let me know by whatever means is most convenient for yourself, and I'm more than happy to help. Thanks, guys.